Hello, welcome to Relative Frequency. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. Let's start with some definitions, always a great place to start in math. When an experiment is performed a number of times, the estimated probability or relative frequency or experimental probability of an event E is the fraction of times that the event E occurs. If the experiment is performed n times and the event E occurs FR of E, so frequency of E times, then the estimated probability is given by P of E is the frequency of E divided by n. For example, I was bored one day. This is not a true story. This is not how my life goes. But I was bored one day and I flipped a coin 50 times, taking note of how many times the coin landed heads up. In those 50 times, I got 37 heads. So my probability is given by 37 divided by 50. The 37 times the event E heads was facing up, divided by 50, the number of times I flipped a coin. As I said, the number FR of E is called the frequency of E, and is the number of times the experiment is performed, and is called the number of trials, or the sample size. Alright, so flipped it 50 times, that's N. 37 times heads came up, that's my frequency of E. I found my probability to be 37 over 50. Experimental, it's what actually happened. Now, let's look at some examples. 400 adults are polled. 160 of them support universal health care coverage. E is the event that an adult does not support universal health coverage. Calculate the relative frequency. It's pretty easy just to say, oh, that's 160 over 400. All right, 160 over 400, but we have to read all the words. 160 support universal health care coverage. E is the event that an adult does not. So if there are 400 adults, 160 do, 240 do not support universal health coverage. Our solution is therefore 240 over 400, which simplifies to 0.6, or 60%. 60% of the people in this particular survey did not support universal health care coverage. Frequency distributions. Let S consist of the sample space marked by S1, S2, and so on up to Sn. The notation P of Si is the estimated probability of a single event Si. For example, maybe my sample space is 1, 2, 3, 4, 5, 6, all the different number of dots that could be facing up when I roll a standard 6-sided die. P of Si is the probability that I roll 2. Maybe 2 is what I want, so probability of rolling a 2. Now, for any individual happening in the sample space, the probability has to be between 0 and 1. Always. 0, impossible event, never gonna happen. 1, guaranteed to happen. Yeah, always happens. If I add the probabilities of all the different outcomes in the sample space, it has to be 1. This is 100%. There's a 100% chance that one of these things has to happen when I conduct my experiment. If I have an event E, which is E1, E2, and so on up to ER, then the probability of all of the event elements added together makes the probability of the event E overall. Right? So I say it way better down here. The relative frequency of an event E is the sum of the relative frequencies of the individual outcomes in E. For example, the following table shows the frequency of outcomes when 2 distinguishable coins were tossed 4,400 times and the uppermost faces were observed. What is the relative frequency that heads comes up at least once? Heads comes up at least once. At least once, let's think about that. At least once is 2 heads, or 1 head, but not tails. So to find this probability, the frequency that I get heads is 1200. The frequency with which I get heads tails is 1050. The frequency with which I got tails heads was 1300. And I add all of these up and divide them by the common denominator of 4400, the total number of times we flipped the coin. And we got 0.8068 if we round to 4 decimal places. 80% chance that will get at least one head, which is interesting because something called the law of large numbers, if we did this maybe 10,000 times, this number will get closer and closer to 75% of 4 different outcomes. I'm looking at 3 of them. Over time, they should all be about equal. We see that doesn't always happen in reality, but that's what the math says. We'll see that in the next section. Following chart shows the results of a survey of the status of subprime home mortgages in a certain state in November 2008. 4 categories are mutually exclusive. So if a house is in foreclosure, we do not consider it to be past due. If it is repossessed, we do not consider it to be in foreclosure. So once it's reached the next stage, there we go. Once again, I did not come up with this example. It is from Weiner and Costanoble. My apologies for stumbling on the name. Okay, so we want to find the relative frequency distribution for the experiment of randomly selecting a subprime mortgage in this state and determining its status. First, we need to figure out how many do we have total. So 115 plus 5 makes 120. 120 plus 60 makes 180. 180 plus 70 makes 250. 250 total mortgages. So the probability distribution reads, if current, 115 over 250, which is 0.46. Past due, 70 over 250, which is 0.28. In foreclosure, 60 over 250, which is 0.24. And repossessed is 5 over 250, which is 2%. Now we can add these up as well. 0.46 and 0.24, 4, 5, 6. That's 70. 98 and 2 makes 1, right? 98 cents, add 2 cents, we have $1. So all the probabilities have added up to 1. That's exactly what we need based on our probability distribution. All the probability of everything in the sample space has to add to 1. What is the relative frequency that a randomly selected subprime mortgage was neither in foreclosure nor repossessed? Not in foreclosure, not repossessed means I'm looking at these values. 115 plus 250, 115 over 250 plus 70 over 250 gives me 185 over 250, which is 74% of the houses. Now, I have this written a little weird here. What's the relative frequency? Yep, no, that's right. I was thinking frequency is the numerator, but I've written it correctly because the relative frequency is when we divide by the total number of trials. This is good. Let's keep going. The following table shows the results of a survey of 200 authors by a publishing company to compute the relative frequency of the given event if an author is specified as chosen at random. So an author is established and successful. Here we see an author. So we're looking at all the authors. Our denominator is 200. What type of author are we specifying? Established and successful. And intersection. Established and successful. There's only 56 out of these 200, which is a 0.28 or a 28% chance that an author is established and successful. Again, an author. So I'm looking at all 200 of them. Is what? I just want the new authors. There's 54 total new authors. It's 27%. An author, so I take all 200 of them, is successful. Successful authors, 72 total. Now let's get into some particulars. Let's only look at successful authors. Alright, successful authors, I'm only considering my top row. There's a total of 72 successful authors. Out of these successful authors, which ones do I care about? Let's see. Let's make successful authors all I care about. And we want specifically established. That's right there. And that's how we get our 56 out of 72. Whereas, and I want to erase these, so I'm going to think about it really hard. Not going to erase those. Now, as an established author, so I'm only looking at established authors. I'm only looking at this column. If you could hear my dog barking in the background, I do apologize for that. My recording studio is a closet, so what can you do? An established author, 146 of those, is successful. So I'm only looking at established authors as my total. I'm looking at these 56 that are successful. 56 out of 146 simplifies to 0.38. It's really important to know what you're looking at as your total. Who are you taking it out of? And once you restrict that view, which portion of those are you looking at? That's it for relative frequency. Thanks for listening.